Okay, then. So now that we have covered the theory about cylindrical coordinates, we have the example 2.17 and the example 2.18. Okay, so we cover its theory, and now we will solve these examples and got more experience and also keep learning about it. So let's see. Let's solve the example 2.17. Okay, let me change the color. Example 2.17. And let me write. Uh, let's suppose that we want um, place on the origin of the reference frame of the hand of the robot um, reference frame of the hand of a cylindrical robot of an cylindrical robot. And the coordinates 3, 4, and 7. So right here we already can use what we have learned on the cylindrical coordinates part 3. Um, these coordinates with this t, which means transposed. Remember that we were confused about um, this example in which it brings to us these statements. The three first columns represent the orientation of the reference frame after a series of transformations, and the last column represent the position of the origin of the reference frame. And we assume that this order for these statements, right here we said that was 1, right here 2, right here 3. So with this guess, so um, for logically, so this last column, which is the fourth column, represents the position of the origin of the reference frame. So let's use this and compare with this example. Right here, the origin of the reference frame of the hand of the cylindrical robot. Um, but as you can see, these coordinates 3, 4, and 7, and as we are referring to a cylindrical coordinate system, so right here, cylindrical coordinates, um, we are referring to um, a system in which will occur two linear motions, which means translations, and one rotation. Those are transformations. So it's going to be two transformations of translation and one transformation of rotation. And we saw on this description, this draw, that the linear motions, the linear transformations, they are R about the x-axis and L, which is on the same direction as the z-axis, and the rotation one, which is with a angle alpha, is not above any um, any axis. It's not above z or x or y, and neither point to a specific direction is is a is a transformation in which we have to use the angle, this alpha angle, and decompose on its components. So it's going to be something like r times cosine of alpha and r times sine of alpha. So, and I write something which is very important as well. This is very important. The order, sorry, not this, about the orientation right here. Rotations change the rotation. So this is very important. So the rotation is the only transformation that has the ability to change the orientation of the robot. If we are doing transformations of translation, which can be above this axis, or even when is outside but point on the same direction, it won't change the orientation, just the position. As I said, for example, if we are right here and we are doing a transformation of translation to this point, what we are changing is the position. If we are right here and doing a transformation of translation to this point, what we are changing is the position. But if we are right here and we do a transformation of rotation, what we are changing is the orientation. And this I commented on the last video, which was cylindrical coordinates part 3. Okay. So let's take something important that we have learned on the last video about transformation rotations. Let me take this, let me copy, and let's use to compare right here, because S is a transformation of rotation and I will call another part important. We have to be, we have to have in mind um, the notation of a rotation uh, on the transformation on the cylindrical coordinate system. So if we are referring to a rotation, let me write this, which is very important. So if we are referring to transformations if we are referring to transformations on the cylindrical coordinate system, so we're going to have two transformations of rotation of translation, and they only change the position and we also have a transformation of rotation. And this change the orientation. So as always says, it's very important to take care with the notation. Uh, it's not something trivial. It's very important to write the correct notation. So right here we are doing a transformation of the P frame of the reference P in relation to the reference R, which is the origin of the reference frame F, X, Y, Z, and we have two reference frames, and one turns into a reference to the other, F and OA or F, okay, and we are also doing a analogy to a robot. Let me take this. And I said that these three first columns was for, let's see, for the orientation, and the last is for position. Now let's see right here, because now as I'm using the book to guide me, we will confirm this. So that is X, Y, and Z. And remember that Z is L, as you can see right here. So let me erase this. Okay. Y is for R, but this is, sorry, R sine of alpha in X, R cosine of alpha. And as I'm seeing on the book, we were right. That is correct. So our guess, or what we assume it was correct, and this validate the part 3 of the cylindrical coordinates. Good. Let's keep going. So L or sine of alpha and or cosine of alpha. But if these three first columns, if this order is for orientation and the last is for position, that is something that we will going to investigate throughout this video. Okay, because if this first three columns is for the orientation and the last one is for position, and I'm saying that the L, the length of L, which is from a transformation of translation and is related to the orientation. So let's say, is the orientation of the end factor. And again, I think I don't need to say all the time at this point, because we are doing a analogy to a robot arm. Okay, so is the orientation of this point. Okay, so let me write this. I'm gonna write that is the orientation of the end effector. Orientation of the end effector. Okay. And this statement of this example asked us to calculate the variables, articulated variables of the robot. So let me write calculate articulated variables, articulated of the robot. And I will use the solution of the book. I don't have problem with this. So what we have to do is define, let me write solution. Define the components of the localization. Of the origin of the reference frame. Of the matrix. The cylindrical, and right here I'm using, of course, I'm using the English notation. And if I'm not wrong, this example is like a continuation of this first example, of this first statement, because um, it asked to us to calculate following this statement, which is this one, um, following this sequence. So we have to use this sequence. So notice that we are solving an example which passed to us now real values of R, which is from the ratio of and of the orientation. Right here we were working with these values, with these generical values. So let's remember, again, very important, and I don't know if I can stop to telling this to you, that this is a analogy to a robot arm. We are doing analysis, thinking in terms of linear algebra, thinking in terms of geometry, but we have to use this thinking, doing an analogy to a robot arm. So this vector, notice that is a vector, but we are doing an analogy to a robot arm. We are mixing theory of linear algebra and introducing robotics context as well. So let me read again. Is a sequence of a translation of R along the x-axis, a rotation of alpha about the z-axis, and a translation of L along the z-axis. So again, this text is a description of the motion that this robot is doing. So right here is a robot arm which are doing a motion, a task based on this description. And I said that we could have a tiny mechanism, a device which has the ability to extract, and after this it it's doing a transformation of rotation about alpha angle, and after this is going to up, but as you can see on this point, it is not above any axis, but is doing a transformation of translation pointing on the same direction as the z-axis. Okay, so we already have write this transformation equation. So let's copy. Okay, paste right here. Let me erase this now. Okay, okay, perfect. So now we got our transformation equation. We got our coordinates. And right here, let me continue this. And localization of the origin of the reference frame of the matrix for the given values. These values. Okay. And now let's also use the matrices to substitute on the transformation equation. So let's copy right here. And thanks to the octave, now we have a tool to evaluate these operations without taking a lot of time. And now you know how the process is done. Let me erase this. Okay. And right here, of course, is alpha. Right here, I place theta. I do not place theta. It comes together when I copy from the this is derivated from the characteristical rotation matrix about the z-axis. If I'm not wrong, but it is derivated from a characteristical rotation matrix, and right here you know that is the W, which is the scalar factor that we add to maintain this matrix on its quadratic form. Okay. Now what we have to do is to substitute these values as you can see on the solution. Define the components of the localization of the origin of the reference frame. Let me just copy. These are the components, and we have already defined it when we do this analysis. So L7 R cosine of alpha is equal to 3, and now R sine of alpha is equal for. And let's keep going. We have the result of this operation. The result of this operation is this one, this matrix. So let me copy. Okay. Okay, right here we will do more analysis, more text interpretation as well. Um, the question is, um, what asked for us is, I do not write this. Right here, calculate, calculate the articulated variables of the robot. What is this? Now it is very nice. Um, let's give us the opportunity to think in a mechanism. Better, I will print a mechanism which contains it not contains the ability of thread, but I will bring a joint, a figure of a joint. And if you don't know, in other opportunity, I will do a video talking about joints, the components which is used in robots. I will bring the image of a joint, a simple joint. Right here. So, wow, what a mess. What a mess. Okay, I will leave right here. Um, so as you can see, there's the links and the joint. Links, one link, another link, and holding together these links, this joint. Okay. And what on a robot arm, what on this structure is articulated? Okay, what makes this articulated is the joint, and the whole system is articulated. But what we wanted to know is the variables of this robot, the articulated variables. So for this description of this example, what is this, the articulated right here? Right here, okay? So guess what? It's about alpha. So we have to use alpha, and both alpha and R, which is from ratio, will determine these variables. And again, which is very important, you have the sense uh, we have to be you have to be able to at this point to dis, distinguish what is a when we are doing changing the position and the orientation. At this point, it has to be obvious to you, and I'm already had explained that. Um, so when we are working with this alpha angle, and of course we have to use the value of the ratio, um, and this way we are changing the orientation. Okay, orientation of this robot. Okay. Okay, so um, we can, for now, we can ignore this, but um, this is the final position and orientation, which resumes on the localization of the robot. And if I'm not wrong, specifically the endpoint, what is important to us. So let's use this. Let's use this information. And also, we have to remember from trigonometry this relation. Tangent of alpha is equal sine of alpha divided by cosine of alpha. And let's use this relation. And it has to be very simple. Even if we had this r multiplying the sine and the cosine, we just have to eliminate this r. So we got back right here. And so is 4 divided by 3. And so tangent of alpha is equal 4 divided by 3. And right here we want to evaluate alpha. So alpha is equal arc tangent of 4 divided by 3, which is equal this number, 53.1 degree. Okay, now let's calculate the values for R, which we are expecting to be the same on this relation. So R is equal 3 divided by cosine of alpha. So R is equal to 3 divided by cosine of 53.1 degree. And let me calculate cosine of 53.1 is equal, and sine of 53.1 is equal 0.8 and 0.6. So if we divide 3 by 0.6, we will obtain 5. So it's 3 divided by 0.6, which is equal 5. And R divided by 4, R is equal 4 divided by sine of 53.1, which is equal 0.8. So 4 divided by 0.8 is equal 5 as well. Okay. So the answer right here is R is equal 5 units. That is the answer. So now we know the limits that this robot can reach is 5 units. So 5 units right here, or this region. It is a ratio of 5. 5 units. Okay. And 5 units and L equals 7 units. That is the answer. So if you remember from the last video about cylindrical coordinates, part 3, we were struggle with where we can place. We we were calculating, guessing, analyzing where this what is the maximum point that this robot, which is stretching, can reach, and we said that is still this point, and now we know that is a ratio of 5 units, and this L as this example 2.17 past was is 7. So now we have kind of a sense of the maximum point that this robot can reach. And we have to conclude that with this matrix, we know the position and orientation. And this resumes on the localization. And I'm going to place under parentheses and the factor. Okay, so is this point right here. Position and look and orientation. Okay, I think for now is all. On the next video, we'll solve the example 2.18. And now you're getting more experience in knowing how to do interpretations and use odd or set of skills to solve this type of problems. And that's all for now. Okay, thank you.